Good evening, everyone. Welcome to the Aquarium of the Pacific. I'm Jerry Schubel, president, and it's great to have all of you with us, even if it's only virtually. We're looking forward to having you back before too long in person. I want to thank our sponsors, Gazette Newspapers, and the Marriott Courtyard, who make this lecture series possible. Tonight, Dr. Julie Lesnik is going to explore the value and potential of insects as food, and she will examine some of our aversions through various cultural lenses. Dr. Lesnik is an assistant professor at Wayne State University in Detroit, Michigan. Her research has been supported by the American Association of University Women and the Leakey Foundation. She was also a 2018-2019 Fellow of the American Association for the Advancement of Science, Leshner Leadership Institute, on public engagement for the topic of food and water security. She has her bachelor's degree from Northern Illinois University, her MS and PhD from the University of Michigan in Ann Arbor, Michigan. She has a very distinguished record of scholarship and public outreach, and it's a pleasure to welcome her to the Aquarium of the Pacific. Dr. Lesnik.
Thank you. Thank you so much for having me, even if it's, remotely from here. But it's really a pleasure to get to share my research with everyone who's able to tune in. So to get started, I figured I'd just give us an outline of where this talk is going. To start, I wanted to just kind of give a brief review of human evolution, but also how we know anything about reconstructing past diets when we are doing paleoanthropology research. Then I want to get into the topic of sexual division of labor. So when you have a society and men and women do different things, and how does that affect how we interpret insects as food? Is there something there when we're thinking about who might be choosing to eat insects, especially from an evolutionary standpoint? And then lastly, I want to take a minute and look at disgust here in what we'll call Western culture. Now, Western culture is primarily, Europe and then the countries that it has greatly influenced. And so we want to understand why we don't eat insects here. We do have to start with Europe because it really is sort of a Western culture phenomenon that we not only avoid eating them, but we have kind of a disgust reaction to it. So to give you just a very brief review of human evolution, I'd like to take this very common diagram that you've probably seen a bunch of times and correct it a little bit. So the diagram on the left is known as the March of Progress. And as a person that studies human evolution, this is a very problematic diagram in its image, but also the fact we call it the March of Progress. What it's suggesting is that we have progressed, that we've tried to achieve this human form the whole time, that we've been striving to be human for millions of years. But that's not how evolution works. Evolution doesn't strive for an end goal. Evolution answers everyday problems, trying to find the best way to survive in the environment that those organisms are living in. And so there is no idea of a direction. People might say things about things being lost or going backwards, but that just means the environment changed. And so then they had to adapt to a new environment. So yes, maybe an ancestor had done that previously, but it's new when it's done again. There may be tools available to you because your ancestors have solved this problem once, so you may be able to solve the problem more readily, but there's no such thing as going backwards, and there is no such thing as having an end goal in terms of evolution. So when I correct the image, what I do is I put a little bit of a time component in it. When we draw diagrams like this, we're working in what we would call geological time. So the older things are further down on the diagram. And so the living things are up at the top. So what you have are chimps on the left and modern humans, us today, all the way up at the top. We are who are surviving right now. So we had a last common ancestor about 6 million years ago that's represented by that star. So 6 million years ago, there was some ape-like organism that we both descended from. So both humans and chimpanzees have had 6 million years of independent evolution since that time. So we didn't come from chimps and they didn't come from us. And so then in that 6 million years, each side has had its own kind of trial and errors, these own adaptations, different species that evolved and then maybe went extinct. We know a lot less about the chimpanzees because they live in tropical environments, and warm tropical environments is not great for fossil preservation. And so we know very little about what speciation looked like along the chimpanzee line. But we know quite a bit what's going on the human side, partially because we have wonderful exposures in East Africa and also in Southern Africa, in regions that are more arid that have preserved those fossils better. So we do know that there are extinct hominins that lived in the past. And so instead of putting them in this progressing line like you see on the left, I'm kind of showing you the temporal appearance of them in this new corrected diagram. And so this will be the diagram I'll use throughout this talk. This first figure is a genus known as Australopithecus. They are the genus that is right before ours in human evolution. So we're the genus Homo. So we're our species is sapiens. So as Homo sapiens, we're the genus Homo. So right before us, shortly after that division, after that split with the last common ancestor that we share with chimps, is a genus known as Australopithecus. Now, Australopithecus in a lot of ways is kind of like an upright walking ape. They are similar in body size and brain size as chimpanzees. But the big thing is that they're bipedal. They walk like we do. And we are very uniquely adapted in our bipedalism. It's very specialized. We had to make a lot of changes in our hips, back, feet, head to toe. We've had to specialize our skeleton in order to do that. So when we find a fossil that is so elegantly bipedal, like these Australopithecines, we know that they are related to us because this is a very difficult thing to evolve. We do deal with, when we're thinking about evolution, thinking about things that evolved because the last common ancestor had it, or thinking about things that evolved in parallel. And so we have to be careful that things can evolve multiple times. But for the most part, when we're looking at the time period around 4 million years ago where Australopithecines are, they are so like us in our bipedal adaptations that it's hard to ignore that they must be really incredibly closely related to us. So they are well agreed upon in paleoanthropology as one of our ancestors. Not everything's very well agreed upon in paleoanthropology, but this is one of those things. So I'm going to start there in our discussion today. So these Australopithecines existed, like I said, sometime in the time period from about 4.5 to about 1.5 million years ago. So they were around for a long time. And there's a lot of different species of them. So they're quite variable. Well, one of the variants is known as Australopithecus robustus, and they are in South Africa about 1.7 million years ago. Now, Australopithecines, in addition to being upright walkers, bipeds like we are, they're also tool users. And so tool using has long been a part of how humans have been identified, at least in terms of the complexity of our tool use. And so we know that Australopithecines were tool users. And at this site in South Africa, it's called Swartkrans, we have these tools that are made of bone. The bone is quite, the artifacts themselves are very fragmented. If you look at the image at the top right, what you're seeing are fragments of bone that I would say in kind of diameter, because these are going to be a tool that you use. The diameter is kind of similar to a Sharpie marker. It's kind of how I think of what it feels like in my hand if I was to hold one of those. But we know it's not just a broken bone like you find anytime just in an ecosystem, in decomposition. What we have here are these bones that have isolated wear and polish up on these ends. So you can see that they come to this point and that it's highly polished and worn up there. So we have almost 100 of these, and they're all highly polished and have that wear pattern at the tips. So there's really no sort of accidental environmental interpretation that is sufficient for describing how so many bones could have this similar pattern. For instance, you wouldn't have 100 bones all perfectly sticking in a river in a way that the river water could give you that wear and polish. So the best interpretation then is that these were some sort of digging implement. And so you can see at the top left, I have this animation of how I think these bones were being used, that they are used as digging implements. And one of those things that they could have been digging into are termite mounds. So the original research done on these tools in regards to termite mounds happened in 2001. The tools have been known for a couple of decades, and they're always just kind of thought of as digging implements. But in 2001, Lucinda Backwell and Francesco D'Erico did experimental research, experimental archaeology. So they got their own bones, made their own fragments, and then they used them as tools. And they did a range of tasks. They dug into termite mounds. They stripped bark off of trees. They dug in the ground for tubers. That's another very common expectation for how these were probably used. Tanned hides, processed fruit, used a lot of different experimental tasks. And what they found is that the most consistently similar pattern on the experimental tools, when you microscopically compare them to the artifacts and the wear and scratch that's preserved on the artifacts, consistently the best match was digging into termites. If you can see this microscope image on the bottom right, and you can tell that most of the lines are quite parallel. They're really moving in this direction. There's not a ton of scarring. Most of the lines are very similar in shape. And so what this is suggesting, and why it's consistent with a termite mound, is that when you dig into a termite mound, you're digging into the soil that termites have finely sorted. Right? So termites are building that mound, and they're carrying that soil around in their mouths. So they're not carrying around rocks. They're carrying around specific types of sediments. And so it's very uniform when you dig into a termite mound. As opposed to when you're digging for tubers, you get two things going on. One, you get a lot of scarring from hitting big rocks that are probably in the ground, especially in South Africa. We have a dolomitic limestone bedrock, so there's tons of rocks in the soil. And so you'd get a lot of big pits and scars. The other thing is, I'm using my pencil as an example, if you could see me up in the corner, but you get a lot of circular motion, right? Think of if you're digging for something, you want to get under a tuber and lift it out of the ground, you're going to kind of have a circular motion around that tuber. You're going to be trying to leverage under and maybe pry. And so it has a lot more striations that go in a lot more haphazard directions. But when you're digging into a termite mound, it's pretty much just kind of one direction. You're just trying to crack the crust of the mound, and then the inner matrix tends to be a lot softer. So it's less digging and more breaking. And so we get that more consistent direction of use. And then we have that finely sorted soil that the termites give you that very parallel and thin striations. So we have these artifacts. This is the first time that now we have evidence of termite, at least acquisition, in the fossil record. In paleoanthropology, we kind of have to be careful because we don't have time machines. Everything would be so much easier if we had time machines, but we don't. And so we have to work with the evidence that's available to us. And so things like, if you asked a paleoanthropologist if they, 10 years ago, actually, well, we're at 2020, so let's go 30 years ago, 30 or 40 years ago. If you asked a paleoanthropologist if they think Australopithecines ate insects, they'd probably say, yeah, that makes sense. But we didn't have the evidence. And by not having the evidence, it means it's not in the literature, which means it's not cited, which means it doesn't get repeated over and over again, and it doesn't become common knowledge, and it doesn't influence the way we think about past diets. So although it was completely logical and most people agreed, we couldn't really talk about it until we had these bone tools. And so that's where I come in. So this was published in 2001. I started my PhD work in 2004. So this was still pretty new and being talked about, and was very influential to me as a new person entering the field in how I thought about past diets. So one thing to note, though, is why did those researchers even dig into a termite mound in the first place, right? There's that sort of element of scientific exploration is that you had to be in the right place at the right time. And so I give a lot of credit to these researchers to even think to dig into a termite mound so that we could see that they match. And so where that idea of termites as a food source comes from is really from the fact that chimpanzees, our closest living relative, eat termites through the use of extractive foraging. So they use tools to pull termites out of their mound so they can eat them. So we know that this is a capacity in a brain, that chimpanzee brains are capable of tool use. And so the last common ancestor between humans and chimps probably had some capabilities in tool use. And so then when you get up to Australopithecines, we know they're using tools. And so to try to think of what they're using those tools for, looking at chimpanzees and knowing what they're able to achieve gives us an idea. Now, they've had their own millions of years of evolution, but we know that tool using is kind of part of our collective condition. And so thinking about termites and chimps, like not only are they tool users, not only are they termites, but another remarkable thing about chimpanzee termite eating is that it's seen across sites across Africa, and it looks different at every site you look at, just slightly different. Some chimpanzees don't use just one tool, they use tool kits. So they have a multiple tool succession that they use in order to extract those termites. Sometimes they modify the tools in specific ways, such as like a brush tip, which can increase the amount of termites they're able to extract. But basically what you're seeing is what we call chimpanzee culture. Now, it's not as complex as human culture, but it is, as best we can explain it, culture. The variations you see across the chimpanzee populations are not explained by environmental factors. So it's not like these chimpanzees go after a different type of termite, so they've developed a different type of tool. They're generally going for the same type of termite. So what you're seeing at these different sites is all of the different ways chimps solved the same problem. And if they're solving the same problem, it means it's an important problem. I kind of think of it similarly to humans and origins of agriculture. It wasn't just one human population that started growing crops and then we all learned from them. Instead, around the world at roughly the same time in the Andes, in Mesopotamia, in North America, we're seeing humans cultivate crops and start domesticating and farming. And so again, food is important. That independently evolved because solving that problem led to greater success. And so that's how I interpret this cultural variation in chimpanzee tool use, is that if they're all solving that problem, it must give them a benefit. It must be worth it to solve that problem. And so that tells me that termites as a food source is important. So here I have a video for you really quick, just to show you some of this termite fishing. I have a chimpanzee here from the Republic of Congo, and she's going to use a tool set. So she's going to come with one tool in her hand and one tool in her mouth. So this is Maya, and she's going to approach the mound. She has that tool in her hand, and what she's doing is perforating. She's opening the hole. So the termites, when they go out to forage, they seal up the hole so that ants can't come flooding in. Now she opened the hole, she grabbed the second tool from her mouth, she's threading it in, pulling the termites out, and she's able to feed. How this works, why this is able to be the right tool for the job, is that what she's eating are the soldiers of all the castes of termites. So termites are very much like bees and ants in that they're social insects. They have a queen and a king that reproduce, and then they have the workers that tend to the mound and go forage, and they have the soldiers that protect the mound. And then you have the flying caste that's going to go off and establish new colonies. So all of the castes are different. They have different morphologies that they evolved. And so the soldiers, being the soldiers, what they do is they pinch of these termites. So these are, I'm just going to go back here and just show this again while I'm talking. And so what we have is that the termites that chimpanzees forage for the most are of the genus Macrotermes. Now, Macrotermes termites, their defense mechanism. So termites have different defense mechanisms. Some of them spit like a gluey, sticky substance. For instance, the number one predator are ants to termites, and so they can kind of immobilize them through that toxin. Or they can just actually cut and stab. So they have the soldier caste of Macrotermes have mandibular pinchers that cut. Now, but they only go in one direction because the soldiers are dispensable. They're never going to put genes into the next generation. Their only purpose is to protect who's in the mound right then. And so they bite and they don't let go. And it's a very effective defense mechanism. But chimpanzees can use that to their advantage because the soldiers will attack any breach in the mound, like that piece of grass that the chimps thread in, and then they bite and they don't let go. And so that's how you can pull them out of the mound without them falling off, and how chimps have a reliable food source once they've adopted that technology. So one thing I'm often asked, though, I believe that if I'm reconstructing the past diet, if I'm looking at what termites hominins were eating, I believe it's this genus Macrotermes, because chimpanzees are strongly selective for it. Humans that eat termites all around the world have more Macrotermes species in their diet than any other genus of termites. And so it's just logically a great place to start when we're thinking about what they were eating in the past. But I've been asked before, how do I know that Macrotermes termites existed in the past? Now, there's a lot of entomology research that shows that the genus Macrotermes has been around for 20 million years, evolved in Africa, roughly paralleling the evolution of humans, filling the same environments. So there's really good literature and research done by others, but it's not in our field. So it's always a question I have to answer. It's always something I cite, but it just really wasn't satisfying for a lot of people, because again, we like to work with the evidence that we have at our sites. So a handful of years ago in Tanzania, in northern Tanzania, at the site of Olduvai. So one of the most famous fossil sites. So this is where the Leakeys made their discoveries. So at Olduvai, at one of the new sites that they opened up, they found this feature that's in the bottom right. And so what this feature, so I, being the termite eating expert in the field, somebody emailed me his picture and asked me, like, do you think that looks like a termite mound? And I thought it did, but the problem for me with termites is that they can they can make their nests under the surface of the ground. So how do you know this is a 1.7 million year old termite mound, not just a modern termite mound that was built in the site? So after a lot of work, one of the biggest things that has convinced me that this is an ancient feature and not a modern one. And it's kind of hard to see in the picture, but you can just see this perfect kind of curve right here. Like, yes, we dug it out, but what you're seeing is 2 layers of soil. That's what we're seeing. And it's in this curve. What this upper layer of soil is ashfall from a volcanic eruption. So part of the reason why we have such beautiful fossil preservation at Olduvai in general is that a catastrophic ashfall killed what was living there and preserved its fossils. So what this is suggesting is that same ashfall fell on this termite mound. And in doing so, it immediately just kind of extinguished all the termites in there, so cooked them. And so all of that termite biomass is still preserved in that soil matrix there that was their mound. So we were able to, me and colleagues, I started working with a geochemist. I went around, I collected different genera of termites and also grabbed samples of the soil from their mounds. And what we were looking for was to see if the chemical signatures of a termite was unique enough to name it to the genus level. So was it Macrotermes? Was it Trinervitermes? Was it Cubetermes? Can you name it to the genus level based on these we call biomarkers? We're looking at hydrocarbon fingerprints. So basically patterns of molecules, the abundance of some versus others. And that creates a pattern or a fingerprint. And we were able to identify to the genus level. We know what the fingerprint for Macrotermes termites looks like. We were then able to look at soil samples that came from those termite mounds and find the biomolecules in those biomarkers in the soil as well. So you can tell, the termite mound to the genus level as well. You don't even need the actual termites. Basically, the hydrocarbons come from their cuticle. And I like to think of the termites when they're going through their termite mound, they're constantly exfoliating, right? If you were to do a scrub to exfoliate, you're going to get sand or salt or something in there rough. So termites are constantly exfoliating and leaving those molecules in the soil. So we can identify the termites to the genus level. We can identify the dirt of their mounds to the genus level. And then because we're super lucky, we were able to pull out preserved organic material from this mound because of that catastrophic preservation. It's been blanketed by that ash and preserved for 1.8 million years. And we're able to get the organic compounds out of there and identify that mound to Macrotermes. So now can I say that they put them in their mouth and actually ate them? Still don't have that time machine. But We do know that this is at a hominin activity site. So we have other fossils, we have tools, we know they were active here. And so if you were active right next to an excellent food source, there's a very good chance that they were eating them. So moving more recent in time, remember, we're not progressing towards the human condition, but we are getting closer to us in time and in relation. So now with this next step, we're at the genus Homo. This is representing Homo erectus on this diagram. Now, Homo erectus is not the first species of the genus Homo, but it is the first time that like real human characteristics, the suite of characteristics that we really identify as ours, start to appear. Bigger brains, taller body size, more complex tool use. Like we're really able to see us in Homo erectus. And so when I'm reconstructing the past diet for reconstructing the past diet for Australopithecines, I use chimpanzees. I use other African apes. But once we get to Homo erectus, we have to start looking at the human condition in order to make sense of what was going on in the past. So this is just kind of a little timeline to show you that brain size increase with Homo erectus. So here were our Australopithecines, so the genus Australopithecus. Here's our first species of the genus Homo, Homo habilis, a little bit bigger in brain size, but then we have this huge jump. So with Homo erectus, things are different. We have a big jump in brain size, one of the biggest ones that happens in a short period of time over the course of our evolution. And so when you have a bigger brain, yes, they're smarter, but the other thing you have to keep in mind is that their resource needs are different. Our brains are energetically expensive, right? They are high-powered machines that we carry around with us, and so they need a lot of calories in order to function. And really, they run on fatty acids, so we need fat in our diets in order for these large brains to function. And fat is actually quite rare in the environment. We're used to having lots of fat in our modern diets because we farm animals. But when you're hunting animals, those animals tend to be very lean. And also hunting's really hard. So fat is a difficult source of a difficult nutrient to find in the natural environment. And we know that Homo erectus must have been doing that. They must be achieving that in some way. So to think about how they're using those brains, though, first, what that larger brain means in terms of sort of intelligence, I've added something. I've added some tools to our diagram here. So the chimpanzees on the left have their foraging sticks. So those are the perforating sticks that they use to puncture those mountains, and then they come in with a second tool to fish. The Australopithecines, that first figure on the bottom, use a technology that's called core flake technology. Basically, they take two rocks and they hit them together in a precise way. It's not just bashing rocks, but so it requires some like knowledge of what they're doing, but it's really just like one strike. Like there's not a lot to coming up with it. They have to have some understanding of the physics, but then that's it. There's like one problem to solve, and they're able to make these tools. So they strike one rock with another kind of at a glancing blow, and that gives you a flake. A flake falls off, and those flakes are really sharp. Those flakes can be used to butcher animals. You can totally disarticulate a skeleton of like a deer or something, antelope, with those tools. The problem is they're very delicate, so they dull really quickly. So that problem being one of the biggest problems. So then you'd have to make a new flake and continue on what you were doing. So kind of thinking of stone tool technology, that quick dulling tool is a problem. And Homo erectus came in and solved it for millions of years. The next tool on here, that kind of yellow stone, is an Acheulean hand axe. These tools, developed by Homo erectus, were used through Neanderthals and early modern humans. They are abundant. We have thousands of them. So it wasn't that like there was just a single tool maker that made tools for the community. We think that most Homo erectus were probably able to solve this problem on their own, or having learned it, were able to, implement it in their lives. And what they do is, it's a technique called bifacial flaking. So you can see that hand axe, and it's kind of like roughly the size of your hand, if you think of it that way. and sort of same shape, right? So it's more tapered at the top, like where your middle finger is. And so how you get that shape is you started with a stone that was rounder, right? And you work the edge on one side in order to get it kind of angling in towards that cross section. And then once you do it there, you flip it to the other side and you take off the edges so that the two sides of that round stone come together, taper into a sharp edge. So it's a much thicker, like the blade edge has a lot more stone behind it. It's not thin and dainty. And so it stays sharper for a lot longer. But also, because it's a big, heavy stone, you can retouch it. You can take your tool again and make it sharp again. So some of these, kind of like somebody who has a favorite pencil, start really big. And then we end up with these like nubbins of hand axes as well in the fossil record. So you know that was one that somebody really enjoyed and they kept retouching it instead of making a new one. So that whole thing, what I'm trying to demonstrate though, is that forethought, that complexity of thought, to know that you have to do things in specific order in order to achieve your goal, in order to have an image in your brain and act in order to achieve it. And so that was a big step in what we're seeing in the intelligence of these hominids, and also why that's what we do, right? Homo erectus was, in terms of their intelligence, is really starting to look like us. So when I'm trying to reconstruct what was going on in the past for Homo erectus, I have to use modern humans, right? Apes no longer work. And so what I do is I look at what modern foragers are doing. So modern foragers are modern humans, right? They might be remote tribes that have very little contact with the rest of the world, but they are fully modern in their physiology, morphology. They are modern humans, same brains capacity and intelligence, right? But they just live in a remote area. But what foragers are doing is they're living 100% off the natural land. And so when we're trying to understand the past, we really kind of have to look to these modern foragers in order to understand what Homo erectus was doing, because you can't look at us, right? We have concrete buildings and electricity and all of these things that our survival and reproduction no longer depends on our ability to extract critical resources from the environment. And so we have to look at somebody who does that in order to understand past behavior. So that's why we look to modern foragers. But one thing that we have with modern foragers is that we have these correlates. So no matter where they are, whether they are up in the Arctic or in a tropical region, these things are true for all foraging groups. One, their size of the group must be small. Basically, if you have to get the resources from the environment, you have to feed you have to be able to feed everybody. So you can easily have a population that gets too big and outstrips the resources in the environment. So the groups stay stable at a pretty small size in order to be able to feed everybody. They also have to be mobile because resources are not equally available in every place every day of the year. And so you might seasonally have to move. You might have to weekly move. So being mobile, not having a permanent settlement is another correlate. Also, we have egalitarian societies for the most part. There might be some respect for elders because they have knowledge that's useful, as younger generations are trying to solve their own problems. But in general, there isn't a stratified society. It's very egalitarian. Basically, if you're not producing crops, if you can't store resources, if the environment is only producing what you need, if you can't store resources, you can't store power. And so for the most part, everybody's egalitarian. But there is differences in how people function in that society. And one of the most consistent is asexual division of labor. Now, this is relevant to edible insects because one of the first quotes that I had read when I was starting to do this work came from a study of foragers in sub-Saharan Africa. And they quote that it would appear that the considerations of gender cannot be excluded from a discussion on entomophagy in terms of what is consumed and who is involved in the gathering and processing of insects. So started to think, okay, do men and women in these foraging societies use insects differently? And so what you're seeing, though, when we're thinking about the sexual division of labor, what we're seeing that's consistent, what the pattern shows, is that it's not straightforward like women hunt that men hunt and women gather. It's not like black and white, like many might try to paint it. But what we see is that men go after riskier resources. And often that is hunting large animals, but women might target smaller animals. It can also be vegetation, mushrooms, for instance. There are mushrooms that grow on the sides of cliffs. Men tend to go after those, while women will go after safer mushrooms. So women tend to target resources that have what we call a low risk of acquisition failure, meaning that when they go out for it, they're probably coming home with it. Men, when they go out hunting for large animals, come home without more often than they come home with. The other things that we see is that women tend to conduct their activities with their children with them. I mean, we do have care in societies and can leave kids, but for the most part, it's just easier if everybody can take their kid and go out. So the part of the lower risk means not putting your kid in harm's way. And then it's also really important when we're thinking about foraging groups that when we're thinking about women in their prime, they don't have a source of reliable birth control. So it means that adult women usually are pregnant or lactating through their adult lives. And so they're going to have those kids. They're going to be more, maybe a little bit more aware of what they're doing because their activities really influence the success of that child. So because this is so widespread, we have some hypotheses about why it evolved. And so these two most common hypotheses are these: the cooperative provisioning model and the conflict model. So the cooperative provisioning model suggests that by targeting different resources, men and women are able to more efficiently extract nutrients from their environment. They're not getting in each other's way. They're likely getting a larger variety. And so that's a really successful way to feed everybody. The other competing hypothesis is called the conflict model. What this is saying is that men and women have different conflicts with their environments. Because they have different strategies of reproduction, they might need different foods. They might need nutrients differently. And so maybe why they're going after different resources is because they're looking after themselves and they're getting what they need. So when we think of these two, the cooperative provisioning model is really a human model, right? That is a pattern that would have only evolved with kind of the human condition, with Homo erectus. The conflict model, where men and women, male, female, go after different things, could be a condition that predates humans by however long. It could be an early primate condition. So we have two kind of time periods looking at this as well when we're trying to solve this problem. Now, in general, paleoanthropologists pay more attention to the cooperative provisioning model because it does work a lot. These hypotheses are not mutually exclusive. I think it's important to remember that you might evolve different patterns for different foods. So for meat eating, for instance, men usually bring back more than they can eat themselves, and so they share it. And so the cooperative provisioning model works really well for meat. And we have tons of evidence of meat eating, and so every time something else is found, it gets published, and our literature is full of meat eating examples. And so cooperative provisioning is kind of how we think about eating in the past. But when we bring in a new food source, we can start challenging some of those basic assumptions that we have about what was going on back then. So in order to kind of figure out, what's going on, we have to look and see what the correlates of insect eating look like in foraging societies. And so just across the continents, we see that women eat insects more than men. In Southern Africa, in Botswana, the Kung San, the quote here is, "When foraging, women may stop and eat termites all day." Right? It's a social thing, but they will also take insects back. They'll take termites back to camp and prepare food for, everybody else. So if you just list what foods are in the diet, you'd be like, yes, women eat termites, men eat termites. But when you quantify it and you take into account that women eat a lot of insects when they're out foraging, they're eating a lot more insects than men are. The Ache in Paraguay, we see that the women average about 15 minutes a day in search of various insects, especially beetle larvae, but they protect it. It's like 15 minutes of insect foraging time. So again, showing that importance. If you dedicate a portion of your day specifically to something, that must have some importance. And then when they're doing other tasks, they'll always opportunistically collect those beetle larvae when they come across it. And then here's a quote from a book on insects as human food. explaining the Aranda of Australia. So here, Bodenheimer says that women accompanied by their children carry digging sticks and go out in search of small fauna, including social insects that are available year round. And so this is really illustrative of what we're seeing in that. One, a simple digging stick. It doesn't have to be complex. And two, that they can carry their kids with them. I mentioned this was Bodenheimer just because the 1951 book, Insects as Human Food, is sort of the tome that we have in edible insects research that we're all trying to kind of update. And so this quote comes from there. So in order to test, so I can take a very straightforward hypothesis testing approach to this. To try to figure out which model best fits the patterns we see for insect eating. So if insects provide nutrients important to female reproduction, and if non-human primate females also consume insects more than their male counterparts, then the conflict model, not the cooperative provisioning model, is the best fit for the pattern we see. So when we're thinking about nutrients, are the females getting what they need? We're thinking about paleo diets, right? So this is the real paleo diet. Now, the trend that we know today is based on a European diet. It is very meat heavy. It has a very niche diet in terms of all of human evolution. For the most part, we've been in the tropics for all of human evolution. And in the tropics, it's much easier to get your nutrients from non-meat resources than to rely so heavily on meat. So it's really important when we're thinking about any paleo diet that the only thing that we can say with certainty is that it was variable. It is variable in space. It is variable in time. So different resources are available seasonally. So if you are truly trying to have a paleo diet, variation, change up what you're eating. You can eat one food all week and then next week eat a different food all week. That would be more representative of the paleo diet than what the trend is that we see people implementing today. So it's impossible to reconstruct an average, but the one thing we know that's true of any paleo diet in the past is that it worked, right? We're here today, right? So they must have gotten the nutrients necessary to survive and reproduce. And so when we're thinking about men and women, this conflict model, we have to think of what nutrients women need. And again, when they're adults, they're probably pregnant or lactating for most of their adult life. And so we tend to think of men needing more protein than women. That's because men have about 8% average larger body size than women. And a lot of that is muscle mass, and muscle mass needs protein. So men do have a little bit higher protein need than women. However, when women are pregnant or lactating, their protein needs go up beyond that of men. And so it's really important to think of protein when we're thinking about women's reproduction and the resources they need. They also just need energy, so fat to just have calories in order to gestate and lactate. It's an energetically expensive activity. And then the micronutrients that you're probably familiar with in prenatal vitamins, right? So folic acid or folate is really important in early fetal development. And so that is a resource that women are going to need when they are getting food for themselves. So just real quick, the insects I've talked about pretty much here so far and what was listed in those foraging groups, kind of look at them for their nutrients. And what we can see is that some insects are really high in protein, have a lot of protein, great source. So if pregnant women are worried about their protein needs, seems like a good thing to do is go get a safe insect meal instead of waiting and hoping that somebody brought you meat home. Like that's the narrative that we've had for human evolution, is that like women are sitting there waiting for men to bring hunted food back. And that makes no sense because then we wouldn't be here. So what makes more sense is that women were actively getting the foods they need, and that when men do come back from a successful hunt, they get more food. And that day was easier. Or it's a very social thing. Bringing back meat brings people together, and that networking is super important. So meat is important, but not the only food that you can eat to survive. These areas that's missing is that we don't have the data for it, not that that those insects don't have that. So edible insect nutrient profiles are kind of new. We're starting to get, so we have a lot of holes in the data still, but more is coming constantly. So just one more example to kind of illustrate that point is that for a group in Northwest Amazon, there's a season of the year where men get about 12% of their total protein from insects, while women get about 26% of their total protein from insects. So they're clearly relying more heavily on them than men. So that's kind of the first part, right? So insects do give the nutrients that women need to survive and reproduce. So then the second part is that primate condition. And so what we see here is that chimpanzees are expert tool users. We've been over that. And it's really the females who do it. Now, this is a picture I was lucky enough to take. This is at Gombe, so in Tanzania, Jane Goodall's famous site. And what you see here actually is that while the female chimp is fishing, if you look closely, she is nursing her young daughter as well. And so this was an amazing moment because this is exactly what I'm trying to illustrate about insects, is that it's a safe way for moms to get food. Also, just a funny story, the best thing was that right before this, while mom was looking for a tool, the baby was having a major temper tantrum, and I had no idea why. I had no idea what was going on. And then as soon as mom settled down, her daughter curled up and started nursing. And so I was like, oh, it made much more sense. But even more amazing is that eventually mom left and her daughter remained. This is the exact same position on that termite mound. And so now her daughter is making her own tool, and she's going to use the hole that her mom was fishing in. So her mom left it so that she can have a successful chance. It's easy for her to go find a new spot, but now her daughter can use the spot that she knew was working. And so she's making her own tool, and she's going to sit there and fish for a while. So we see that female chimpanzees eat termites more than their male counterparts. Part of this is because daughters stick closer to their moms than the boys do. The boys have to go find their place in the social hierarchy. That's what they need to do to survive. But finding food is of primary importance to females. So the daughters stay close to their mom, and they become expert termite fishers as well. So this is well known in chimpanzee literature. It's kind of discussed as maybe a tool using condition, right? Like less about the insects and much more about the tools. And then we see something similar in orangutans. Orangutans also use tools to forage for termites. They just do it high up in the trees. And even though that seems like a pretty great risk when you have your baby to be up there using a tool in the tree, we still see females do it more than males. They might not do it as much during certain parts of a child's life because they are riskier, so they'll like slow down at certain parts of certain times, but we still see that female orangutans eat termites more than males. And then we can go to gorillas who are not tool users, and they still eat termites, and it's the females that eat the termites more than the males. Now, finding insect eating in primates can be difficult. When they're using tools, it's easy to see. But when they're just picking them off the ground, you don't know if they're eating a leaf or a berry or a bug. So it's a lot harder to study insect eating in these smaller monkeys. But anytime a study was able to tell how much insects males eat versus females, it was the females that ate insects more. And so in the monkeys that are most closely related to apes, like mangabeys and langurs, evidence suggests females eat the insects more. And then in the monkeys of South America that are even more distantly related to us, capuchins, squirrel monkeys, the data shows females eat insects more than males. So we've confirmed it, right? The conflict model is the better fit when we're considering how insects are used in past diets. And so thinking about this pattern, it really helps to go all the way back to about 50 million years ago, to the last common ancestor of all of the monkeys and apes living today. And that fossil primate was an insectivore, ate a diet that was almost 100% insects. So our ancestral condition is to eat insects. And then as monkeys diversified, they had to fit different niches. We couldn't all eat insects all the time, especially as body sizes get bigger. You can't live off of insects alone. So they started adding different things to our diets, like leaves and fruit. And it was probably the males that were trying those new resources, and the females would rely a little bit more heavily on the tried and true and trusted resource, those insects. So this pattern has probably existed, in certain populations of primates for the last 50 million years. Just a funny note there. So we think of foraging males are, riskier and going after meat. Well, in today's society here in the US, when I do bug tasting events, we still celebrate men today for being risky. And so then eating a bug in the US tends to be what's considered risky. And men tend to eat insects more readily at bug tasting events than women. Now, it's not perfect. Plenty of women eat bugs. Here I am. But it is kind of funny to just see how we reward risk and how men might be doing it just for that showiness at an event, but that might not mean anything in terms of if they'll actually adopt insects into their diet. So talking about insects for us, why don't we eat them? Not only do we not eat them, but like we hate them. We hate the idea of it. We're disgusted by it. And so why is that? I want to leave you with that. So evolutionarily, when we're talking about this as a term of Western culture, we're talking about Europe and then us and all the places Europe colonized and had continual relationships with. Europe was under ice until 18,000 years ago. So talking about the paleo diet trend, eating meat is necessary in Europe because there isn't vegetation under that snow that we can readily eat. But if we can eat the deer that can extract nutrients from the bark or the dead grass, we can make lives for ourselves. So it's a specific northern latitude adaptation to eat meat. And so insects were probably not an important part of the early human diet in Europe because they just weren't available. That is my time. And so looking at this pattern, this is number of insects consumed per country. And so you can see it's largely a tropical resource. The darker countries have more insect consumption and they are closer to the equator. So I've run these numbers. There's a beautiful gradient, right? So you can predict insect eating by your position of latitude. So the further away from the equator you are, the less likely you are to have insects in your diet. The problem is the environment might explain why we never adopted insects, but it doesn't explain why we have a negative reaction to insects. And so that's been my most recent research question. And this really comes to the idea of ethnocentrism, which is something in anthropology we train hard to be able to get through this, right? We all tend to judge others by our own standards. We all view the world through our own lens. We tend to think if it's different, it's wrong because I made a decision to do something and I would clearly never do anything that was wrong. So if you did something different, you must be the one that's wrong. That is a very kind of common mentality. And so as anthropologists, and we try to help people just try to implement this in their lives and just become more accepting of other cultures, we try to eliminate that bias and understand a culture for what it is, what they value, instead of us putting our own values on it. But we have a lot of that bias to overcome. And so a lot of this goes all the way back to our colonial history here. If we think of Columbus coming here from Europe, up in Europe, in that ice-covered, or in strong winter seasons, insect eating was never really a part. They were, a big, strong meat-eating culture, so insects would be relatively redundant. So it just wasn't a food. If they had any associations in 1492 of insects and food, it would be that animals ate them. They might have an association of it with spoiled meat, but never really probably gave a thought much to insects as food. However, when they travel across latitudes like had never been seen before and arrive in the Caribbean, where people look very different, where people behave very different, they have very different traditions and societies and foods, and they look so foreign to these Europeans that came, the reactions were strong. And so here's one quote from one of Columbus's companions on his second voyage. They eat all the snakes and lizards and spiders and worms that they find upon the ground, so that to my fancy, their bestiality is greater than that of any beast upon the face of the earth. Now, we know what happens next. We know the genocide and the overtaking of the land and everything that happens after European colonization here on the land of North America. And so part of that rationale, the justification that the Europeans used for doing that to the humans that lived here was that they viewed them as beasts. They dehumanized them, and they used insects as part of that. And so our bias against insects is still rooted in this. And so we need to remember that when we're thinking about why we don't eat them. Now, the thing, though, is that you might be like, but my stomach churned. Like, that's a real response. How can this be cultural if it's making me gag? Well, the disgust is real, but disgust is an emotion we learn very young in life. A kid at 2 will put anything in its mouth. And it's the reactions of the adults going, oh, don't do that, that teaches kids what's disgusting. It might be trash. It might be in the toilet. It might be disease salient and important for them to avoid. And we need to communicate to that. And so we teach them what's disgusting. But when we do that with insects, that's not actually true. If a kid's trying to put a bug in their mouth, instead of going, ew, that's disgusting, try, that one's dirty. Let's find you an insect that we know is safe to eat. That would be a better response that could change an entire generation's way of thinking. And so if we're going to make insects a possible resource here, we have to stop those negative reactions. We have to raise a younger generation for this to be viable, for them to have this food source for them, because it's them that's going to have to be battling the resource depletion that we are leaving for them. Water especially, it takes over 20,000 liters to produce a kilogram of beef, an edible mass of kilogram of beef, and it takes about 400 liters to produce that for insects. And so when we're trying to think of smarter ways to use our resources to get the same nutrients in order to support our growing population sizes, insects are a really great idea. And so we need to change how we talk about them. We don't need to eat them. You don't want to eat them? You don't need to eat them. But trying to keep that opinion from filtering down to the younger generation would do a lot of people a lot of good. If this was interesting to you, I do have a book. It is from the University Press of Florida, so I suggest you look them up online, but you can find it at large booksellers online as well. If you're interested in trying something, getting cricket powder online, this is my favorite cookie recipe. And so I gave you a link there that you should be able to look up pretty quickly. It's just a tiny URL for bug cookies. And you can get my favorite cookie recipe. So thank you. These are my other references in addition to my book that I use kind of in my discussion today. And I look forward to having some time talking with Jerry. So thank you.
Thank you, Julie. You've made me very hungry. Now,
Perfect.
I lived in Detroit many years ago. In the mid to late 50s, the population of Detroit was about twice what it is today. Detroit's making a remarkable comeback through innovation, creativity. They're a leader in urban agriculture, where they've turned vacant lots, and there are lots of them, into places to grow food. And I understand they also have a cricket farm. Is that right?
That is right. We do. We have Detroit Ento here is our cricket startup. And that's one of the beauties of insect farming is that you can do it in a city. It doesn't require a large footprint. You don't need large pastures. You can stack things vertically. You just need the bin that you would have a population of crickets in, and your production increases by the number of bins you can have. And if you can find a way to store those bins vertically, you can do this in a pretty small footprint.
And is it true that termites, if properly prepared, taste very much like popcorn?
Yes, I think fresh termites with a little bit of salt taste a lot like popcorn. I do like to qualify, though, that like popcorn, they're much better fresh than they are when they're a little bit older.
So sometime when we have you back here live, we'll have some of your cookies or some termites. Detroit also makes the best coffee I've ever had. Have you ever had Detroit Bold?
Oh, yes, absolutely.
It's the best coffee going. It's named after different streets in the city. Woodward Avenue is the main thoroughfare going downtown. There's 8 Mile. All some of the best. I have to ask you, when you invite people over for dinner, do you occasionally slip a few crickets into their salad?
I do. I never give insects without people knowing that insects are in their food. One, allergies is a legitimate fear. It's possible that insects trigger the same reaction for people who have shellfish allergies. So I tend to always put a warning if I'm serving cookies to be aware that it can trigger a shellfish allergy. But the truth is we don't know a ton about insect allergies. And I was really scared of that. I've been doing bug eating events now for at least 6 years. And I, at the very beginning, was terrified of reactions. I make sure I have Benadryl in case, put up warning signs. And I've been doing these events, and my friends and colleagues have been doing these events, and there's no horror stories of somebody having this severe reaction. So I actually think it's really quite rare. And this is going to be, don't expect this where I'm taking this. I actually think that insect allergies are going to be quite rare because we already eat quite a bunch of insects. So our bodies are already used to it because by eating processed foods, we have a lot of allowable parts per million of insects that the FDA allows in our food. So we've already been exposed to chitin and all of the insect parts. And so that's how you prevent allergies, is through continual exposure. And so I think that has helped us in adopting this as a new food.
And it's very clear that we are going to have to change our diets going forward, because we can't continue to produce food the way that we have, with the growing population and with climate change reducing the productivity in many of the areas where population is growing more rapidly. Fortunately, those are the areas, though, that do have lots of insects, right?
Yeah. Yes, absolutely. And so it is a weird, like, it's funny because insects right now, with sort of climate change going on, we're seeing a lot of loss in insect species diversity. So there is a bit of an insect apocalypse going on right now. So the idea of going out and foraging insects is not the greatest, because we can do more harm than good. But farming insects and cultivating them, then you're not doing that same level of harm. So you can get your sort of base insects that you can use to start your farm, but that is going to be the most sustainable way instead of wild foraging.
And the insect farming doesn't take up much space, doesn't take up much water. You don't have to use pesticides and herbicides, so there are a lot of advantages.
It really is, like, all of the problems that we have: greenhouse gases, land use, water use. Like, it sounds absurd that insects are really the answer to so many of them. Like, it sounds like a simple solution to this big problem, that it makes it unbelievable, but they really do solve all those problems. It's just the cultural thing that's going to be this barrier for us to take on this super remarkable resource.
Are you an ento-vegan?
I don't eat a lot of meat in my. I love that you brought up that term. So ento-vegan is like what I like to call the gorilla diet, right? So gorillas are actually vegetarian, with the exception of insects. So the only animal-based food in their diet are insects. And there are humans today that are vegans that have added insects into their diet, and they consider themselves ento-vegans. I'm not that extreme in my diet. I'm much more of a flexitarian, if I had to pick a word. I eat as little meat and animal product as I can, but I'm pretty weak sometimes, and I have to kind of weigh other things like price and stress and what my job's doing. And like, sometimes the strict vegan diet just doesn't work for me. So I've had to find something that's been more sustainable for me. And so it's just generally a reduction of all animal-based foods. But the ento-vegan diet is an amazing way. If you are looking to do as little harm as possible to animals, then the ento-vegan diet is actually really appealing. Why people pick, so whether you're a vegetarian, vegan, a lot of people use a lot of different philosophies in why they're doing that. And they measure their impacts differently. So there are some vegans that would never eat insects. Some vegans measure their impact by number of lives lost. But if it takes 3,000 insects to make a pound of food, that's a lot of lives lost. So there are vegans who would never consider insects. But some vegans consider harm differently than just life lost, and instead might be based on quality of life. And so there's or an environmental impact. And so if you are a vegan relying heavily on soy products, you have a lot of the negative impacts of a soy industry, the farmland use, the number of animals that are killed in the farming equipment. There's a lot of negative impacts from eating plant-based meat alternatives. But if you can kind of know what your impact is because you're eating farmed insects, like their sentience is lower, right? Their their nervous systems aren't as complex as ours, right? So there's a lot of ways that you can justify insects, even if it is a vegan diet, if you change your definitions a little bit.
I can remember being at a lecture a long time ago by Ed Wilson, the famous ant scientist, and many other fields very famous. And a lady asked him, Professor Wilson, what do I do if I see ants on my kitchen floor? And he paused and he said, well, they love chocolate chip cookies, so if you have some, crumble some up and put it on the floor and watch them. Now, maybe what he should have said is catch them and have them for dessert.
Right. Well, and it's funny, people ask me all the time, like, did I grow up loving insects, right? Because I have a very different relationship with insects now than your average American. And I didn't like bugs particularly, but my mom would always, if there was a bug in the house, she'd grab a glass and a postcard and humanely take it outside. So I definitely grew up with a very different respect for insects than a lot of people. And so I think it was easier for me to kind of endear myself to them and think about them in a different way.
Our mothers have a big impact in that. Our older daughter used to have an iguana. It was about 3 feet long, and its favorite food was crickets. So we used to buy lots and lots of crickets. Unfortunately, a lot of them would escape, and they'd be all over the darn house. Now in Japan,
that is the problem. That is the problem with them. But yeah, Dad, if you've had pets that eat insects, like there's all these sort of things. Like if you're more comfortable with insects in some other form, you're probably more likely to think about them as food. So if you feed them to something, like you already view it as a food source and not just a pest.
That's right. Julie, thank you for an outstanding lecture. We really appreciate it. I hope we'll be able to get you back here once we're able to have lectures live, and keep up the good work. Thank you very much. Good night, everyone.
Thank you so much.